Material science and engineering is about understanding different materials and how we can process them to make things. Here at Loughborough, we have a variety of equipment that help us learn about industrial processing. You've probably heard of injection moulding. It's a process used to make a variety of everyday objects, from this kettle to the sole of this shoe, and things you probably haven't thought of, like the dashboard or the bumper of a car. Tom is one of our demonstrators. How does injection moulding work?
Well, the principle is actually fairly easy. We start off with some polymer pellets like this. They're in a hopper and they fall down into a screw. They fill the screw with a known volume, and that volume is equal to that of the mould. When it's melted and we're ready, we ram the screw forwards, we fill the mould, allow it to cool, and we can peel out our pieces.
Currently, the machine is set up to make these pieces. As you can see, there's one already in the mould. The bit we're really interested in are these. These are the test pieces. But what's the remainder called?
The remainder is simply the sprues and runners that are used to guide the material into where the piece is. Once we're finished with that, we grind it back up, place it in the hopper, and it goes through the process again. What can go wrong? Well, if we fill it up too much, we can end up with something called flashing, where we have excess material around our pieces. And if we don't fill it up enough, we don't complete our piece.
Why is this piece a different colour to the kettle?
All we do is we add a small amount of pigment, and we really don't need a lot, and we can make pretty much any colour that you want.
Can we see it in action?
Sure.
So that's injection moulding, and you can tell things have been injection moulded because of this dimple.
Yeah, even much larger items like this bin on much larger machines, and that little dimple is a sign of where the material was injected.
But I have these, and they don't have a dimple, which means they must be made another way.
Yes, commonly using a blown film line, which I can show you. So here we have our film blowing line. We have some polymer pellets in another hopper that drops down into a barrel with a screw that leads on to an annular or circular die. We then blow air into this bubble, which is held in place with nip rollers at the top that then control the speed at which we're hauling off. Once we get the material at the end, and you've got your bag of sweets, we can control the properties so you can get to the goodies on the inside.
Here at Loughborough University, our lecturers are experts in material science and engineering, working with industry. Sina's been working on a new project that will allow us to build wind farms in new places. What problems have you faced during this project?
So we'd like to be able to create more green energy in the UK, and wind farms are one of the options that we have to create more green energy. Now, wind turbines are massive structures. They're about 100 metres tall, the length of a football pitch, and their blade could span the length of an A380 airplane. How much renewable energy do you think we are creating now in the UK?
10% of our energy.
About 10%. Let's have a look at the National Grid Live status. So this is the status of today's generation of energy. So you can see about 38% is coming out of renewable energy and about 31% out of wind farms. The wind turbines are massive structures. They can create a lot of clutter on the radar screens. So that means if you've got an aeroplane flying over an offshore wind farm, it is difficult for the radars to distinguish between the two because there is hundreds of kilometers of clutter on the radar screen. So in this project, we looked at developing coating nanocomposite materials that would allow us to build wind farms closer to airports, military bases, and weather stations.
So how did material science and engineering help with this?
So radars work on the basis of interaction of materials with the electromagnetic field. So we developed a nanocomposite material which would interact with both magnetic as well as electric field. Obviously, you need to have different components to the material system, hence the name composite. So we started with a a starting material like these granules of composite material. Then we did some smart processing to them, and we created different types of shapes looking at different properties of composite system. So I can show you how our material system behaved on the radar screens. Do you want to have a go?
Yeah.
Okay, so let's pick up that metallic plate. We take it as an example of a wind turbine. These massive structures will have a lot of metal and steel in them. Now if I take this portable radar and I point my radar onto it, you can see on the radar screen that is the signature of this metallic plate on the radar screen. Now let's put that black tile over it. So that's our composite material. Now we're putting it over the metallic substrate, and let's look at it on the radar. So you can see the signature almost disappears. Now if you remove the black tile, you'll see what is underneath. That was one material system that we looked at. We looked at another material system for more complex geometries of the blades. That's the white one. Would you like to try that one? Okay, so same. So we'll put that over the metallic structure, try the radar. You don't see anything on the radar. If you remove that, there it goes. So that will allow for the uptake of wind energy in more places, onshore and offshore.
So your work spanned over materials, science and engineering?
Yes, from fundamental understanding of physics of interaction between materials and electromagnetic field, to the chemistry of polymers and composite materials, as well as engineering challenges in developing materials and coating technologies for complex shapes such as wind turbines.
So material science and engineering is about understanding the different properties of materials that come from their varying chemical compositions, structures and processing, and how these properties translate into their performance in real-life applications. I hope you've enjoyed this quick look around material science and engineering at Loughborough. We look forward to welcoming you here soon.